Hello, today we're going to talk about the natural exponential and logarithms in base 10. So the first thing we're going to look at is the natural exponential. So if you look to the right, you will see that there are different graphs of various exponential functions. All of them are written in the form of y is equal to a to the power of x, where a has to be any number that is greater than 0. So whenever we have exponential data that is observed or used in the STEM, in the finance fields, the base is usually written as the letter E. And the letter E is approximately 2.71828. And it's very similar to the number pi. So if we wanted to find out what this E value is, if you cannot remember this, you can press second on the calculator and press the ln button because you see e to the power of x there. So when you press second ln, you will end up getting e to the power. Well, e without an exponent is actually e to the power of 1. So e to the power of 1 is, like I said, approximately 2.71828. All right. So that is what the number or the letter E is in its rounded state. So now let's look at logarithms in base 10. So here it says that the logarithm in base A of B, so if I write it out, I'm going to have the log in base A of B actually means that we're trying to find the power that A must be raised to in order to find B. So here I can say that we're going to take A and we're going to raise it to some power, which we can call X, and we're going to find or equal B here. So what I can say here is that my log base A of B is equal to whatever that X is. So this is what we normally use as our conversion between logarithms or logarithmic form and exponential form here. So for this lesson, we are going to focus on logarithms in base 10. Okay, for right now. We will do other bases in the other lessons, but we're going to focus on logarithms in base 10 for right now. So the first thing that you need to understand too is that anytime we have something written as in log of base 10, there are two rules that we are going to focus on. The first rule is going to state that the log base 10 of 10 to the power of x is going to be equal to x. The next rule is going to state that 10 raised to the power of log base 10 of x is also equal to x. So what is happening essentially is that the base of the power, which is that 10 here, and the log with the same base are going to cancel each other out to leave you with the exponent. Just like in rule number 2, my power is 10 to the power of log base 10 of x. So my power, the base of it is 10, and that 10 is going to cancel with the log base 10 there, giving me just x. So example 1, they want to see, without a calculator, they want us to find the log of 10,000, and then they want us to find the log of 0.01. Well, before we get into finding the logs, you also need to understand that anytime we have a log base 10, that is the same thing as just saying the log. It's the regular log. So the 10 is understood. It's very similar to having a square root. We don't write the 2 on the root. We just write square root. We don't write the 2. So this 10 is understood here. So anytime you just see log of some number, you already know it's automatically in base 10. So for example 1, it says find the log of 10,000. Well, since I already know that I'm dealing with log of base 10, I'm going to write this as log base 10. And I know that my log of base 10 is going to cancel out with an exponential expression with the same base of 10. So 10,000 is the same thing as saying 10 to the power of 4. So if I say 10 to the power of 4 here, I get 10,000. So I can rewrite this as log base 10 of 10 to the power of 4. And from here, I know that the log base 10 and the 10, that's the base of my exponential part, is going to cancel out, and I'm going to equal 4 without using the calculator. For part B, I can rewrite this as log base 10, and 0.01 is going to be equal to 10 to the power of negative 2. So if I have 10 to the power of negative 2, you will end up seeing that I get 0.01. So I can rewrite this as 10 to the power of negative 2 here. So 10 to the power of negative 2 is basically saying I'm taking 10 and I'm dividing it by itself 2 times. Because remember, an exponent means multiplication repeatedly. So if your exponent is positive, that means you're multiplying repeatedly. If your exponent is negative, that means you're dividing repeatedly. All right. So of course, my log base 10 is going to cancel with the power or the base of the power, which is 10, which is going to end up giving me a negative 2 there. So that is how I find the log without using the calculator. So example 2, it says use your calculator to write the numbers below in the form of 10 to the power of x, where x is correct to 3 decimal places, not 3 significant figures. We're talking about 3 decimal places, so be very careful. So if I look at part A, it says that we want to rewrite 500. Well, I know that 500 is equal to 10 to the power of log of 500. Remember, anytime we do not have our base written on the log, it's an understood 10. So I know that that 10 and that log base 10 will cancel out. Okay, so I want to rewrite this in this form. So all I have to do is put in my calculator. I press the log button and I press 500. And I end up seeing that we're going to have that this is going to be approximately 10 to the power of 2.699, because it says to 3 decimal places. Okay, it says to 3 decimal places. So here I will end up having this as my answer. Just like I did part A, I'm going to do part B. I want to rewrite 3. So I know that 3 is equal to 10 to the power of log base 10 of 3. Because I know that the log base 10 and the 10 as the base of the exponent is going to cancel. So if I just put in my calculator the log of 3, I will end up getting that I will have 10 to the power of 0.477. So that will be my answer in the form of 10 to the power of x there. And then last but not least, for part C, for example 2, I know that I'm going to have 0.09. That's going to be equal to 10 to the power of log of 0.09. The base 10 and the log with the base of 10 is going to cancel out, of course, so I know that those are equivalent. And then I can just type in log of 0.09, and I end up getting a negative 1.046, 3 places after the decimal. So that's going to be 10 to the power of negative 1.045, or excuse me, 56, if I do 3 decimal places. So here, that is my answer for part C. Now for example 3, it just says use a calculator. So using the calculator is very easy. So if I want to use the calculator to find the log of 40, I literally just type in log of 40 and I end up getting that I have 1.602 or 60 in 3 significant figures. Likewise, I can find the log of 4, which is just 0.602 in 3 sig figures by using the calculator. So now for part C, it says show that the log of 40 is equal to the log of 4 plus 1. So anytime they tell you in IB to show that means don't just give us the answer. I know that the log of 40 is equal to the log of 4 plus 1 because if I type in the log of 40, like I did before, I get 1.602 and it's going to continue. And then if I type in log of 4 and then plus 1, I get the same exact thing. It's not about telling them that they are equivalent. We can use the calculator for that. We need to show why it is equivalent by using properties that we know. So the way that you would do this is you would start off with the log of 40. And then you would say, okay, well, I know that the log of 40 is the same thing as saying that I would have the log of 4 times 10. Because I know that I need a log of 4 somewhere. So once I have that, I should know that this will be equal to the log of 10 to the power of the log of 4. Because I know that 10 to the power of the log of 4 would just be 4. And I can say that this is the same thing as 10 to the power of 1. Right? So now because of we have the laws of exponents, you should know that when you're multiplying like bases, you should add the exponents. So I should know that here, this is just the same thing as saying the log of 10 to the power of the log of 4 plus 1. And because I know that my log base 10 and my base of 10 on my power cancel out, I already know that this is equal to the log of 4 plus 1. So that is how I can show that process, right? So now for my last example, example number 4, it says that the magnitude of an earthquake, which releases E joules of energy, is given by the equation M is equal to 4/5 times the log of E divided by 10 to the power of 2.3. So part A, it says find the magnitude of an earthquake, which releases 5.1 times 10 to the power of 10 joules of energy. So they told us that the magnitude is M and the energy that is released is going to be E joules of energy. So here they told me I have 5.1 times 10 to the power of 10 joules of energy. So here they gave me E. So all I have to do here is substitute in 5.1 times 10 to the power of 10 for E. So I'm going to have M is equal to 4/5 times the log of 5.1 times 10 to the power of 10 divided by 10 to the power of 2.3. So when I write this, I can literally just put it into the calculator. So I will literally type in my fraction, which is 4/5, and then I will type log and then open up another fraction and I will do 5.1 times 10 to the power of 10. And then in the denominator, I'm going to put 10 to the power of 2.3 and close my parenthesis on the end. When I do that and press enter, I will end up getting that my answer is approximately 6.73. That is going to be the magnitude of the earthquake. So for part B, it says how much energy is released by a magnitude of by magnitude 3.7 earthquake. So if we have an earthquake that is 3.7, okay, in its magnitude, what we're going to end up having to do is we are going to plug in 3.7 for our M. So we're going to have 3.7 is equal to 4/5 times the log of E, which is my energy, divided by 10 to the power of 2.3. So in order to do this, you could, of course, do it by hand by using your inverse operations. But what we are going to do is we're going to put this into the equation solver. So in order to get to the equation solver, we are going to press math, and then we are going to go to solver, and we're going to put the left side of the equation in the part that says E1, and then we're going to put the right side of the equation in the part that says E2. Now, if you wanted to, you could have put the left side of the equation in Y1 and Y2 by pressing Y equals and find the intersection on the graph, but you will have to zoom in or zoom out, and it can be a little cumbersome. So this is just an alternate way that you can solve an equation. So I put the left side in E1 and the right side in E2. And remember, I got to this equation solver by pressing math, and then I went all the way to the end for solver. You can solve pretty much any equation here. So when you do that, you're going to press graph for OK. And then in order to solve for the X value, where it's hovering over it, you already know it's not solved, because if it was solved for, there would be like a little box to the left of the X, just like when we use the TBM solver to find values. So you have to press alpha, enter, and then you will end up seeing here that that's what X would have to be here. So we know that E would have to be approximately equal to 8,413,951.416. All right, that will be how many joules are released. But of course, being that they gave us our, if we look in part A, they gave our joules in scientific notation. We are also going to give our answer in scientific notation here, as well as three significant figures. So here I can say that E, or my energy, is approximately 8.41 in 3 sig fig times 10 to the power of 6, because you will have to move your decimal 6 times to the right in order to get it back to where it was. So that is our answer here. If you have any questions on the natural exponential, or if you have any questions on logarithms and base 10, please let me know, and I will be more than happy to assist you. Have a great day.